Right. So this is question 4. It's a laser question. As we'd expect in a laser question, quite a lot of explaining probably to be done here. So it's a 4-level system with various arrows showing transitions. We've got the ground state at the bottom here, this top level T, and then U and L, the upper and lower levels. So label the transitions associated with pumping. So pumping takes electrons from the ground state to the highest level. So that is this one. And stimulated emission is from the upper level to the lower level. So that is this one. The wavelength is given here. Calculate the energy above ground state of level U. So the output radiation from the laser, this wavelength we can use to calculate a photon energy. That photon energy must match this transition that I've poorly labeled II. So what we're using then is E equals HF combined with C equals F lambda to give us E equals HC over lambda. The wavelength we're given, so we're trying to find energy here. So 6.63 Planck's constant times 10 to the minus 34 times speed of light divided by this given wavelength, 1.05 times 10 to the minus 6. That gives us the photon energy for this laser. So let me just grab a calculator. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 1.05 times 10 to the minus 6. I've got 1.9 times 10 to the minus 19. That's a number of joules. So that tells me the size of the transition from level U to level L. I've got that level L is 0.3 times 10 to the minus 19 above ground state. So I simply need to add the 2. They're both times 10 to the minus 19. So 2.2 times 10 to the minus 19 joules is my answer. Okay, part 3 then, what triggers a stimulated emission event? So that happens when an electron in level U is passed by a photon of the appropriate energy, and we have just calculated that energy, causing it to fall to that lower state. So what triggers a stimulated emission event? When an electron in level U is passed by a photon of energy equal to U minus L. Which causes it to fall to L. Causing that electron to drop to level L. That should secure us 2 marks. So how does this stimulated emission produce light amplification? So it produces a second identical photon. And what feature makes this? What feature of stimulated emission makes the laser's output coherent? So the produced photons are of the same frequency and in phase with the photons that cause the stimulated emission. Something like that should secure our mark. So part 4, TU is the time spent by an electron in level U before spontaneously falling to a lower level. TL is the time spent by an electron in level L before spontaneously falling to the ground state. So why is it an advantage for TU to be much greater than TL? So this is a question about population inversion, basically, isn't it? So if TU is much greater than TL, then you have a larger number of electrons in U than L, which therefore causes population inversion and therefore allows stimulated emission to happen more than absorption. So I don't know how much of that we need to say for just 2 marks, but I'll try and keep that as brief as I can. So if TU is much greater than TL, and there are more electrons in U than L, brackets population inversion. It's probably important to have that phrase in the answer. Which means stimulated emission is more likely or happens more often than absorption. Okay, so semiconductor lasers are cheaper and more compact. What advantage do they have in terms of energy over other types of laser? Well, they're much more efficient. So they are more efficient, so less energy is wasted as heat. Whoops, that's not how you spell energy. Although with my handwriting, it's hard to tell whether my spelling's correct or not. And I think that's it. That's question 4. Okay.